This video I want to discuss drive sprockets on your vehicle. We just put some generic sprockets on our models just to make sure everything fit together, but now we got to really figure out what the size of those sprockets is going to be. So the selection of sprockets is really important to how the vehicle is going to perform. It's going to affect how the vehicle accelerates as well as the maximum speed. If it's geared too low, it's going to accelerate really quickly but have a very low high speed, and vice versa. If it's geared too high, it'll have really poor acceleration, but ultimately if you could get it moving, it might have a very high speed. We want to try to find something that's a good ratio for kind of a normal kind of performance for our vehicle. So the one way to do it is think about maximum speed, because we know what the engine is capable of, the maximum RPM that the engine will output from the engine, and we also know what our goal is. And so I'm going to do an example, and I'm going to assume that I want my maximum speed to be around 25 miles an hour, which is a good ballpark for a small vehicle like this. You really don't want it to be too fast. For one thing, you'll have really poor acceleration if you're not careful. So in this example, excuse me, I'm going to have a maximum engine speed of 2,500, and that comes from the manufacturer. So you'd have to look up for your particular engine, what's the maximum RPM. My vehicle has a 13-inch diameter tire, and on the CVT, which is attached to the motor, that's the output of the motor, I've got a 12-tooth sprocket. For that size CVT, the manufacturer sells either a 10-tooth or a 12-tooth. So what I'll do is kind of work from the engine speed and see what that gives us. Now we know that the engine will, hang on a second here. That the engine, the max is 2,500 RPM, and that stands for revolutions per minute. What we need to do is somehow convert that into a speed. The speed, for example, typically what we're looking for is miles per hour, which is miles per hour. So here we have revolutions per minute, miles per hour. The minute to hours is easy. It's how do you get revolutions into miles? What you want to think about is your tire on your vehicle. So here's your tire. If you were to take and roll that tire, how far would it travel in one revolution? And that's what the circumference is. Circumference is pi times d, and that's the distance around the tire. So that's what we'll use. So let's start with 2,500 revolutions per minute. And let's look at what our tire is capable of. So it's pi times d, so in my case it's 13. Make sure you write all your units. It's 13 inches for each revolution. So what happens here is revolutions cancel out. So now I've got inches per minute. The rest of it is really just conversion. So if we have 1 foot, we know that that's 12 inches. So inches cancel. Now I have feet per minute. And I know for 1 mile, there's 5,280 feet. So feet cancel out. So now I got miles per minute. All I got to do is convert minutes to hours. So I know there's 60 minutes for 1 hour. Minutes cancel out, miles per hour. And then do the math there. And it's 97 miles an hour. So ta-da, our little vehicle is going to go 97 miles an hour. That's really not possible because there would be no gear reduction. The engine would not be able to produce enough torque to even get the vehicle to move. If you pushed it down a hill or something, I suppose at some point, but you're probably going to have a bad day if you go 97 miles an hour on a little vehicle. So what we have to do is think about a gear reduction and how we can make that work to get to the speed that we want. So again, with our goal of 25 miles an hour, so that's our goal, we have a theoretical max of 97 and our max goal of 25. So let's look at that ratio. So we'll call it a gear ratio, but it's a ratio of sprockets. So if we take 25 miles an hour over 97 miles an hour, the ratio is 0.258 to 1. So it's 0.258 to 1. Now our design is going to look like this. We're going to have, here's the motor. That's going to have a little sprocket on the CVT that goes to the driven sprocket on the jack shaft. And that's going to go over to a driver on the jack shaft that goes to your rear wheel, and that gives you your final speed. So we're going to have CVT sprocket, sprocket on jack shaft, sprocket on jack shaft, sprocket on your wheel. So we've got to do some calculations to figure out what size sprockets. And the way we're going to do is by using that ratio right there. Now, as I said earlier, the CVT can either get a 10 tooth or 12 tooth. If we use number 35 chain, which is pretty good for what we're doing in terms of power. For shaft mounted sprockets that you would use on your CVT, they go up from a 10 tooth to about a 40 tooth. There are larger than 40 tooth, but they start to get just too big in diameter. For the hub mounts, and that's what's going to be on the rear wheel, you can go from a 53 tooth to an 85. So we have to work with everything in that range, and that range to get to the speed. And it's really going to be some trial and error. Now there are some online calculators that you can play with, but just do it manually. So what I did was just, again, I started with the fact that on the CVT, we're going to have a 12 tooth. And then I said, okay, I want something that's reasonably close to 12. And I started with the 16 tooth because the 12 is a very, very small sprocket. And that's really tough on the chain too, because the chain has to turn it around such a tight radius. So it's not a good idea to have a 12 driving a 12. So I went with a 16. So here I have a 12 tooth, and there I have a 16 tooth, and that gives me a 0.75 to 1 ratio. And then for N3, which that's this one right here on the jack shaft, I said, let me use a 20 tooth. Oops, I should have put tooth on all those. And let me use a 20 tooth there, then a 53 tooth here. Now again, I went through a couple of iterations to get these ratios, but the 20 to 53 is a 0.38 to 1. So I have a 0.75 to 1 and 0.38. If you multiply those two, you get a 0.285 to 1. And remember what our goal was. That was very, very close to our goal there when we looked at the 90s, the 25 divided by 97. So now if we take that 97 mile an hour speed, that's with no kind of gear ratio at all, and we do it times 0.285, that gives us 27.6 miles an hour. That's really close, and I'd be very happy with that. I could change one tooth on something in this group here, and it probably would get it exactly 25, but I'm very happy with that 27.6 mile an hour speed. So here's the results. The CVT will have 12 tooth. The driven sprocket, that's the first sprocket on the jack shaft, is 16 tooth. The driver on the jack shaft, so that's the second sprocket on jack shaft, is 20. And the rear wheel is going to have a 53 tooth. And that's going to give me a maximum vehicle speed of about 27.5 miles an hour.